Hello, everyone. I'm Luisa Capagnolo. I'm a postdoc at Boston University, and I work in the research group of WINLI. In this talk, I will show some evidence of sub-relativistic electron precipitation associated with EMIC waves. I will start with a brief introduction and then explain the motivation and goals behind our study. I'll also show the data sources and methodology that we've used, and then move on to the core of the talk, which is focused on two different case studies of precipitation events resulting from two different magnetic conjunctions. And then I'll finish up by showing a comparison between observations and quasi-linear theory. So as we know, wave-particle interactions affect the radiation belt dynamics, either leading to particle acceleration or particle loss. For this specific AGU session, we're focusing on particle precipitation, which we know can occur when particles interact with waves and they fall into the upper atmosphere of Earth. We're focusing specifically on electromagnetic ion cyclotron waves, or in short, EMIC waves. And an example of these EMIC waves is shown in this figure here. The frequency range of EMIC waves is typically between 0.1 to 5 hertz, and they can occur in different bands. For example, these waves are hydrogen band EMIC waves, while these ones are helium band EMIC waves. EMIC waves are excited during ion injections from the magnetotail or solar wind pressure changes. And the reason why we focus on EMIC waves is because these can play a major role in the loss of radiation belt electrons. And additionally, they can also scatter protons. We know that the radiation belt environment can cause many space weather effects, but the electron precipitation itself can also produce some space weather effects. For example, there can be enhancement of atmospheric ionization levels, and even the chemistry of the atmosphere can be changed when there's electron precipitation. Quasi-linear theory and electron dropout observations have shown that EMIC waves are mainly interacting with MEV electrons, but there has been some more recent indication that actually the precipitation could potentially extend to sub-MEV energies. Henry et al. In 2017 showed a statistical study of precipitation events as observed by Pose. And this one here is a histogram as a function of energy where the precipitating electron flux was peaking. So here you can see that the majority of these events was occurring at energies between 200 to 500 keV, while only a smaller percentage of events was occurring at approximately MEV energies. As we know, studies so far have often used Pose, which have some limitations, and so these satellites specifically prevent us to directly measure the minimum energy of precipitation. And so what we're trying to do in this study is addressing this question. Can we directly observe the full energy range of electron precipitation due to EMIC waves? And then ultimately, can we also understand what are the properties, so the energy, the location, and the extent of electron precipitation due to EMIC waves? As far as data sources, we're going to use LEO satellites for particle precipitation data. Specifically, we focus on the Firebird 2 CubeSats, which observe electrons between 225 and 1 MeV of energy. And then we also use the post-Medoc constellation, which, as I mentioned, has been often used for precipitation studies. These satellites can observe 700 keV electrons and 3 MeV electrons. Additionally, they can also measure tens to hundreds of keV protons. For the waves observations, we're going to use either Van Allen probes, the GOES satellites, and also some ground-based magnetometers. And the way that we're combining all of these multi-point measurements is through magnetic conjunctions. And a magnetic conjunction is that configuration in which two different satellites are threaded by the same magnetic field line. So together with magnetic conjunctions, we're also going to use other nearby satellites or ground-based stations to support our observations near the conjugate location. We're also going to provide some comparisons between observations and quasi-linear theory. So the talk is going to focus on two different case studies. The first one is a Leo conjunction between Firebird and Pose. And in this study, we're going to use proton precipitation as a proxy for emic wave activity. And we're also going to study the precipitation evolution, both in time and in location. And then the other case study is instead a conjunction between Firebird and RBSP, in which we actually have in situ wave data from RBSP-A. And so we can run a simulation of quasi-linear theory and compare with the precipitation data. So starting from case study number 1, this one is again a Leo conjunction, and it's occurring between the Firebird Unit 3 and the METOP-01 satellite. So now we're going to take a look at the data of METOP-01. From the top, this is the proton flux at different energies, then the relativistic electron flux above 700 keV, and then the ultra-relativistic electron count rate above 3 MeV. The Pose satellites are equipped with 2 different telescopes, which allow us to observe the trapped population, which is here indicated in the dotted line, from the precipitating population in the solid line. For this specific case, METOP-01 was observing precipitation of protons, relativistic electrons, as well as ultra-relativistic electrons. And this precipitation occurred simultaneously, which essentially tells us that this is a typical emic-driven precipitation signature. Now we're going to take a look at the actual conjunction. So from the top, I'm showing the L shell, solid line for FU3 and dashed line for METOP-01, and then the MLT. And so as you can see, these 2 satellites were in tight magnetic conjunction. Then this panel here is showing the electron flux observed by the Firebird Unit 3 with different energies, with different colors indicating the different energies. And so we can see that Firebird was also observing some precipitation about 30 seconds earlier in time, because at that time, Firebird was crossing a similar region as the region where precipitation was observed by Pose. In this case, though, Firebird was observing precipitation down to 265 keV and up to 1 MeV. It also observed another patch of precipitation here right after the current sheet scattering boundary. So the precipitation for this case occurred approximately at L shells of 4 to 4.5. MLT was approximately 21. And the delta L, or the extent of this precipitation, on average was approximately 0.3. So what we've done next is use the other nearby satellites to look at the electron precipitation nearby the main conjunction. And so here is a polar plot, LMLT, where the sun is here to the left, and we're showing the location where the other satellites observed precipitation. So here I'm showing the electron flux as a function of L shell in this case for the Firebird CubeSats. And again, the different colors are for different energies. And then the other panels show the data from the Pose satellites that also observed precipitation. The black lines indicate the 700 keV electrons, and in red, we're showing the above 3 MeV electrons. The main conjunction that I showed in the previous slide is shown here shaded in blue. So what we can tell is that precipitation, which is marked here in gray, was lasted in that event for almost 2 hours. It was overall bursty, so very localized, but it also spanned almost 1.5 L shells and covered over 2 hours in MLT. During these events, emic wave activity was also observed at ground, and this one here is an example of one station that actually observed emic waves at ground. Now we're moving on to the case study number 2, and this case study, as a reminder, is a magnetic conjunction between Firebird and RBSP-A. So we're going to start to take a look at RBSP-A data. So to start, we have the AL index, which shows that there was a substorm ongoing during this event. Then we have the density, the electric and magnetic spectral density, which show that His and magnetosonic waves were present during this event. Then we have the ellipticity, wave normal angle, and finally the emic wave spectrum here. And these waves are occurring both in the hydrogen band and in the helium band. In terms of location, so the LMLT plot, RBSPA was crossing this region here, and the thicker line is indicating the extent of the emic waves here. RBSPB was also crossing a similar region, but did not observe any emic waves, while the GOES-15 satellite instead actually observed some signatures of emic waves before 2UT and here after 3UT. There were also a few ground-based stations that observed emic wave activity at ground, and here are 3 examples of them. And if we map these stations onto the LMLT plane, the emic waves are going to be approximately at 18 to 20 MLT. The vertical lines here are indicating the UT conjunction between the RBSPA satellite and the 2 units of Firebird. And so if we plot the location of Firebird during the conjunction for this event, these 2 satellites were crossing this region here approximately at 18 MLT. So now we're going to take a look at the data during the conjunction. So specifically the L shell is going to show that RBSPA in the dashed line and FU4 and FU3 in the solid lines are showing actually that the L shell conjunctions was very tight, while instead the MLT was a bit off. We're talking about almost 2 hours in MLT. And then here at the bottom, I'm showing the electron flux observed by the 2 Firebird CubeSats. Again, different colors represent different energy. So what we can do next is use the L shell extent of the emic waves observed by RBSPA and project it on top of the trajectory of Firebird. And so what happens is that this extent is going to highlight the regions where precipitation observed by Firebird was the most intense. And for both cases, for both satellites, we can tell that the precipitation was occurring from 250 keV up to 1 MeV or so. Since we have in situ observations of the waves, we can actually use quasi-linear theory to compare between the expected precipitation from the in situ wave parameters with the actual precipitation observed by Firebird. So we're going to use quasi-linear theory in hot plasma approximation because the wave power of these waves was quite high, approaching the gyro frequency of helium. And here are the pitch angle diffusion coefficients. On the top, the emic waves, and at the bottom, the His and magnetosonic waves, which as a reminder, were also observed during the conjunction. So we can see that the diffusion coefficients are the strongest for emic waves, which tells us that these waves are actually dominating the scattering. And it seems that helium band emic waves can only precipitate above 4 MeV electrons, while instead the hydrogen band emic waves can also precipitate 1 MeV electrons or so. So we've seen that instead Firebird was observing precipitation not just at MeV energies, but also at sub-relativistic energies. So this remains unexplained by quasi-linear theory. So now just a quick summary. We've used a combination of LEO and equatorial satellites to study the electron precipitation driven by emic waves. The main conclusion is that the electron precipitation was observed by Firebird 2 from 250 keV, so at sub-relativistic energies, up to 1 MeV in association with emic waves, both near and after dusk. This conclusion is also confirmed for many other Firebird precipitation events. And here is the reference if you want to look at that study. So from case study number 1, the LEO conjunction, we were able to use proton precipitation used as a proxy for emic wave activity. And we've also seen that precipitation was rather localized, but it lasted almost 2 hours in UT and also covered quite a broad L shell range of 1.5. Case study number 2 instead provided wave observations in situ, and the precipitation was the most intense right where the emic waves were located in terms of L shell. The fact that we have in situ observations allowed us to run a quasi-linear theory. And so we're now able, from quasi-linear theory, to explain why Firebird was observing precipitation of MEV electrons. However, this theory is not sufficient to explain the precipitation that Firebird observed at sub-relativistic energies. Thank you so much for your attention, and I look forward to the live session and your questions. Thanks so much.